The wild new trick that lets a single atom of a thin material, what's this material called, John?
Molybdenum disulfide.
Or MoS, acts like a semiconductor, a metal, a superconductor, or an insulator just by steering potassium ions with a custom transistor. Think software-defined materials where voltage, not a factory, flips the physics. What's going on here, John?
Yeah. So, yeah, this is cool. So, like, the scientists have, with molybdenum disulfide, this ultra-thin layered material that can act like four completely different electronics. So, it can act like a semiconductor, which is like the chips in your phone, a metal to conduct electricity, a superconductor to conduct electricity with zero resistance, or an insulator to block electricity. So the core discovery here is that they demonstrated unprecedented control over molybdenum disulfide's electronics properties through potassium ion intercalation. So let's call it MoS₂, sub-2, naturally exists in two structural phases. So the 2H phase and the 1T phase. So researchers built a field effect transistor, or FET, device that precisely controls potassium ion insertion between the material's atomic layers. So the phase transition occurs at a critical threshold of approximately 2 potassium ions for every 5 molybdenum atoms. So that's crazy. It triggers an abrupt structural transformation from 2H to 1T phase. So what makes this discovery extraordinary is that by fine-tuning the potassium concentration and temperature, they can achieve 4 distinct electronic behaviors from the same base material. This blows me away how this can work like this, right? What are your thoughts on this, Craig? Do you think this is like straight sci-fi? Do you think this is cool? What are your thoughts?
This is really cool. This is definitely straight sci-fi. Yeah. And it's hard to get your head around when you start really thinking about, a reconfigurable material could replace several fixed parts, channels, interconnects, isolations, even cryogenic links, simplifying designs and enabling adaptive on-demand performance. Like long-term, think about better research tools, or near term, sensors and niche cryogenic systems. Longer term, think about thinner adaptable electronics that reconfigure for, battery life, speed, or security at runtime. So we're talking about some amazing types of technologies and things you can do when the material, what it acts like, is your choice.
Yeah. And so beyond scientific interest, right? This discovery, this is what I like about this. It opens pathways for neuromorphic computing devices that can reconfigure their function based on computational needs. So traditional electronics, obviously they require different materials for different functions, but this approach enables a single material device with multiple operating modes. So also, because we love quantum, this work also advances quantum device engineering, because where different electronic phases could be spatially patterned on the same chip. So for example, superconducting regions could provide lossless interconnects, while semiconducting regions handle logic operations all within the same material, which just is absolutely nuts. Again, this is like, how practical is this? We're still in early research phases. So the technique uses standard semiconductor fabrication methods, but the main challenges are operating temperatures, which I think it's like in the Kelvins, and scaling to larger devices. But the principles could lead to room temperature applications as we better understand the physics.
Yeah, so, superconductivity requires deep cryogenics of negative 268 degrees Celsius or so.
Yeah, so for this, the temperature was set at 80 Kelvin, or minus 193 degrees Celsius.
There you go.
Yeah, so, sorry, different phases, different temperatures. So
yeah,
finding the superconductivity in the 1T phase was at 5 Kelvin, so minus 268 degrees Celsius.
Yeah.
Yeah. So we're ways off until we can get that room temperature working, but I think this is the right step. Now, could this replace current electronics? I would say rather than a replacement, I would think of it more like a complementary revolution, enabling new types of devices currently thought impossible with the current technology. So, I think, and based on what I read, we're about at least 10 years, if not 20 years out from something commercially viable.
Promising progress of the wafer scale MOS exists, 2-inch monolayers right now, but uniform growth, transfer, and reliability remain hurdles. So transition to consumer devices likely years away, not months.
Yeah, like we're talking 10, 20 years. But that could be reduced as new scientific insights come, as we advance our understanding of quantum materials, that could accelerate this getting to commercialization phase quicker.
So, go ahead.
No, go ahead. It's a lot. Like this is one of the more advanced tech that we've covered in a while, I would say.
Yeah, and you have to really get your head around the switch between a semiconductor and an insulator and a superconductor, and metal behavior versus non-metal behavior of the material, and the practicality of some of that is very interesting.
Exactly.
There's sometimes
because we've learned that like conductors and insulators are two completely different types of material. Like one can't be another, right? And so this is crazy. Not only a conductor, but a superconductor, which is zero. Oh wow! Why can't I think of the word? Anyways, zero resistance. There we go.
Yeah.
Jeez, it's too early. I'm excited for this, but again, I can't get too excited because we're 10, 20 years out from anything. So, but I'm curious to know where this goes in the next couple of years, if it advances at all.
Yeah, and these breakthroughs contribute significantly to superconductivity research and next generation electronics. And the versatility of this MOS could lead to electronic components that adapt their properties based on operating conditions or user requirements. And you map this kind of thing to, we were talking about changing 3D interfaces where you could put your hands on the steering wheel or something and the buttons would form where your hands are, or you change a setting and a dial that comes out of the glass you can turn or adjust or what have you, or that kind of thing. You pair that with this and you've got some very interesting, the shape can change, a lot of things can change about it, as well as what the device can do.
Imagine this with that. Remember that little robot that could morph or could melt? It was behind bars. It melted and moved out of the bars. Remember that?
Yes.
Yeah. Imagine mixing that with this.
Yeah. We
I think now you've got the the
1000.
The T1000. Is that the liquid one?
I think so. Yeah. The T800 is Arnold.
Okay, so yeah, the T1000, the liquid Terminator. I think that's where we're at if we combine the two.
So, is this the future? Liquid Terminators on the way, along with Skynet and all the quantum and AI, and this is the beginning of the end? If silicon was about shrinking transistors, MOS phase control is about editing reality on a chip, a voltage knob for matter itself. Continue to watch this space for more on this and see where this goes. We'd love to hear back from you.
Yeah.
So, what do you got going on, John?
Yeah, so coming out in September, definitely gearing up for Elevate. I know you're a partner with Elevate, aren't you, Craig?
Oh yeah, absolutely. So definitely we'll be doing something during the Elevate a week, probably a flowgrammer event, if nothing else. They're a partner of ours. Definitely go out and check it out. There's a lot of great events going on related to Elevate. I said great events, sessions, program. Check out their schedule. Check out all the different lines of programs and stuff. There's always good things there. So definitely go check out Elevate. And check out Toronto Starts for our startup drinks, our startup investor drinks, and our Flowgrammer events where we help people learn how to automate things in their business. And John, if people need funding, where do they go?
Yeah, come find me on LinkedIn. I just posted some news about the Shred program, but come find me on LinkedIn, send me a message, and we'll set up, we'll talk and see if it makes sense to find some non-dilutive funding for you.
Really appreciate everyone taking their time to watch or listen to this week. We'll see you again soon.
Thank you.